All right, welcome back. So we finished up our first half on using and programming our system. Went over the command line, software engineering tools on the command line, went over the system actually using our kernel, using system calls. We had our midterm, and now for the second half of the class, roughly, we're going to be talking about compilers. We're going to go over compilers in a very basic way for this week, and then we're going to work on the back end of a compiler, and hopefully we'll understand what that means in a couple of lectures. We're not going to do a full compiler here. If you're interested in that, there's a 5,000 level course, compiler construction, that I teach that you can take. But we're going to look at largely the back end, how it interacts, how the compiler interacts with your system software. But before we get started, we had our midterm last time, as hopefully all of you are aware. I have the small list of people who need makeup exams. I'll reach out to you and schedule that soon. If you missed it for any reason, especially if you have an excused absence, let me know as soon as possible. Grading is underway. Grading is not complete as far as I know. And you'll get an update on that STEM when grading is complete. I think we're most of the way through. The multiple choice was auto-graded. Short answer was sort of auto-graded, but we're double-checking those. And then, of course, the programs need to be checked by hand. All right, any questions before we begin? Sort of questions about the midterm that I didn't cover, or questions on homework, questions about system software, logistics, anything? Yeah.
The SAS quiz was like cut midway through, like from online to paper.
Right.
Like the paper one be graded again? Or
Yeah. So the paper. Yeah. So for those who are in SAS, there was a snafu with timing. I don't know exactly. That was my first time doing this. I added the time as expected, and the system said right how much time you have, but then it didn't give you that amount of time. So we switched to a paper exam midway through, and yes, I have all the paper exams from SAS. And we'll grade those. Did you fill out all the answers or just
I filled out all the paper ones, but
Okay.
The one that got submitted online, I think you have to like put all my responses.
Yeah, that's fine. We have all the paper ones for SAS. So yeah. So don't worry about that.
I have different answers on the paper one from the online one. Will the paper one be counted over?
Yeah, I was planning on just grading the paper ones, but let me know if you want otherwise. But yeah, I plan on just grading the paper ones. And I'm recording. Okay, any other questions, logistic questions about the class, projects? Okay, so speaking of projects, what is it? A little over a week and a half away from the processes project being due. Any questions about that? Everything going smoothly with that? You should have all of the test cases that are publicly released and descriptions of the rest. Yeah. Yeah. So let's make sure what I said here. Yeah, so if the command is successful, then prompt the user again. The shell terminates when there's no more input or there's an error. So it says it here. Yeah. Oh, does it say differently?
It says to run successfully, the program should exit with the exit code of the program being run. I don't know if you're referring to like a command or
Pass the trust. Oh, I see what you're saying. Yeah, that's a good point. So yeah, you don't need to do this. We're not going to test whether you're reporting should exit with the exit code. Oh, you're right. This is contradictory. Good point. Let me just remove this. You don't have to worry about this. I don't think there's anything. What's that? Yeah, you can just continue prompting, just in a while loop. So I had originally had some more complicated error checking stuff in this project, but I removed it and I'll only check non-error stuff. Yeah, go ahead. All of these errors?
Yeah.
Yeah, I guess I can remove this too because you don't need to actually check errors. So you should check these errors anyway, but then just keep prompting the user, if that makes sense. So I basically removed the error checking stuff. So for grading, this is what we're going to test, and none of these have those kinds of errors. So you should be doing error checking with your system calls, but you can just continue prompting or exit if there's an error. But we're not going to test it. So basically, I had error checking stuff in here. I didn't remove all of it, but I kind of at the last minute removed the error checking stuff because it'd be pretty onerous. So I'm only going to check correct inputs for it. So do error checking for the syscalls for sure. But if you have error checking code in there, it shouldn't hurt anything. You can just continue prompting the user or exit. We're not going to test the error conditions. Yeah.
I noticed that the bash script is stripping the last line from my shell. Is there a reason for that? 'Cause that's
What do you mean tripping the last line?
like there's hash dash n dash one that
Uh-huh.
strips the last line.
Oh, strips the last line, yeah.
Yeah. And then outputs to a file.
Right.
And that's like causing problems with the output. Because like
Oh, the reason I was stripping the last line is because of this. The command is successful, it prompts again for a command. So you should have another prompt. That's what I'm stripping in the output, if that makes sense. Did anyone else have an issue with this? What was that? Yeah, so that's why the test scripts are taking removing the last line. Other questions on processes? Anything else? So I do test the tests on my implementation of the program, but that assumes that my implementation of the program is reflected here. So if something's not clear, let me know. Ask on EdStem and let me know. Okay, bless you. Okay, so we're here starting at compilers. Let me go over homework 13 first. Questions about homework 13? Yeah.
Pseudocode, how code-like did it have to be? I just wrote 4 lines of English, not 4 lines.
Yeah, 4 lines is fine. I mean, that's what we had in class, so that's fine.
So it didn't have to look like code. It could just be saying what to do.
Yeah, and the pseudocode I don't think is a rigorously defined term. So
Yeah, that's how it's.
if you do, human language descriptions of the steps, that's totally fine. And homework is graded for effort, not correctness. So that allows me to elide an actual definition of what pseudocode is. But I said just a few lines. So if you had 4 lines, that's fine. And I think I had the algorithm in the lecture notes anyway. And you'll be writing this algorithm for the. Or you are writing this for the processes project. So basic steps of a command line processor. I think that was in my lecture notes. So this was it. This is the maximum I was looking for. The minimum, I guess, I was looking for is, these are the steps of what bash does or what shell script does. This was just to kind of remind you of what's available for you for string tokenization. What functions are available for tokenizing strings? Let's see, standard library. String toke, str toke, and then write an example program that tokenizes a string by spaces and stores the tokens in an array, etc. So this was just asking you to take the string toke example that I gave you, which looped, spacing is bad here, but it looped over each token in the string and just printed it out. And all I was asking you to do was just make an array or make a data structure or make a linked list. Did anyone have questions on doing this? Yeah.
So on that while you're passing no
Yeah.
just stays on the string token.
Yeah.
The string token has state in it that remembers.
Yes, string toke has state, which makes it what's that? Yeah, it's a little ugly by kind of today's standards. But if you look at the string toke man page, it tells you on the first code of string toke, the string to be parsed should be specified in str, So that's str. In each subsequent call that should parse the same string, str must be null. So yes, there's like some static variable or some state inside of the library that only allows you to do string toke like one at a time. That answer your question? So yes, it does have that. It does have that state. That's why I just gave it to you, because it's kind of onerous. Yeah.
Can't really use string code for like multiple strings at once. Like you have to like use the whole string that you want to and then go on to another string.
Yeah, you'd have to do it. Yeah. So not a super great option. So as when we go into compilers and you have to do lots of parsing and string tokenization, this is not a great option for that. We use a fancier tool that I'll go over. Well, you'll actually play with today with a project to do more sophisticated string parsing. Other questions on? Oh yeah. So this question was basically, can you make an array? Can you make a linked list? And can you populate that array or that linked list? Yeah.
Were there multiple tokenization functions? It said helper functions, but I can only think of string code.
Oh yeah, that's a good point. Yeah, I guess I was only thinking about string toke. I guess string toke, yeah, should be helper function.
I thought it might be a trick question.
No, it's not a trick question. Homeworks are not designed to be like tricky. There are other string manipulation functions in C that you could use. So I guess I didn't want to restrict you to if you wanted to go out and find others. So one, did anyone try using an array to store the elements? All right. So for those who use an array, how did you allocate the size of the array? Did you just pick a number? Could make it really big, but so depending on the size of your input, really big may be too small, right? So if you have any constant size, did anyone use dynamic arrays? Someone used dynamic arrays. So a couple ways to solve it is you could parse the string twice, or tokenize the string twice. Tokenize it first to count the number of elements in the array, and then allocate space for yourself. You could reallocate the array dynamically as you loop through the array. Did you guys learn dynamic array resizing? Okay, I think everyone learned this. Or you could use a linked list. You could use a linked list. So who used the linked list approach? Who used the array approach? Who used the dynamic array approach? Who just didn't do it or didn't try? Okay, most people didn't. So that doesn't cover the majority of people. But okay, so I asked this, in case you have questions, because you're going to need this for the processes project. But if you don't have an issue, then okay. But you can ask on EdSTEM if you have more questions about this. All right, so that's homework 13. Any other questions on homework 13? All right, so just be aware that there's no homework 14. So the homework 14 is named after the lecture number, not after the, it's not a count or a sequence. So there's no homework 14. There'll be a homework 15 today. So I put it in the web courses, so hopefully that won't be too confusing. It was really because I wanted to be able to number the videos sequentially, but not have to number the homework sequentially. That's why that's like this. Okay, all right, let's take attendance. Okay, so let's start into compilers. So first, let's start looking at what programming language implementation is. So the first question is, can your processor, like your x86 chip, your ARM chip, can it run C code? Who says yes, it can run C code? Who says no, it can't run C code? Okay, why? Why can't it run C code? Or what does it run? Yeah.
It can't really run anything if it's just on its own. It's not plugged into anything.
Okay, I guess what you mean by on its own. Let's see everything else being set up. Let's say it can run a program, and you prove it runs a program, but you pass it C code. What will happen? Yeah. It executes machine code, not source code, right? So this is how you run your C programs, right? You run this mysterious program, GCC, and you pass your source code to it, and then you have to run this other command for some reason. Well, if you weren't aware, this hello program, this is in machine code. This is in the instruction set that the processor can run, and it's a different file, and arguably, in some sense, a different program from hello.c. They're related. They're supposed to be able to do the same thing, and that's what the compiler will try to enforce for you. But it's a different program. It's a different set of instructions. So what GCC does is it takes source code, C code, and it converts it or translates it, changes it, produces another program, a different program. And that program is in a different language. It's in machine code. And so that's why, this question that I've pestered you with several times, what is a program, what is a process? So what is a program? A program is just a sequence of instructions in some language. And here we've got two programs. We have the hello.c program and we have the hello program. These are two distinct programs. They're in different languages. One's in C and one's in machine code in a specific executable format. What the compiler does is it tries to make sure that the input program and the output program match in terms of their behavior, that they do the same thing. They're equivalent. We won't go too much into, there's sort of some theoretical, interesting theoretical points about the equivalence of programs. We won't get into it in this class. Instead, we're going to look at how you can actually implement this kind of translation or this kind of language processor that will give you the output of the program that you expect. Okay, so there's two types of techniques generally in language implementation, compilers and interpreters. Who's heard of interpreters before? What's an example of an interpreted language? Python. Compiled language, what's an example? C. So some may argue that the language itself is not compiled, but the tool to implement it is. But anyway, these kind of fine shades of details we'll get to in a graduate class. Yeah.
What is Java?
Java, that's a good question. So Java is in some sense both. So Java, the language, is compiled to a virtual machine code, bytecode, and then that virtual machine code, bytecode, is interpreted. So Java is sort of like a hybrid between compilation and interpretation. So compilation and interpretation, for most language processors, they aren't strictly one or the other. Compilers are doing a kind of interpretation, like constant evaluation, and interpreters are often designed to first have a compilation stage. But again, these are details more appropriate for, say, a graduate class. But let me go over the kind of basics of what compilation and interpretation look like. Okay, so compiler, just like we saw when we run GCC, it takes our C source file and it produces an executable file. The executable file contains machine code, and that machine code is then run by your processor or your CPU. So these are our machines, and these are our files. And whatever input you want to give to the program, this is processed by the CPU through the hardware that you learned about in computer organization. This reaches the processor through hardware, along with this machine code, which is running on your hardware, to give you the output of your program. So for instance, when you ran or when you write, say, a program to compute the square root of a number, you write that program in C and you first translate it into a machine code. And the machine code and your input, whatever you ask for from the user, is given to your hardware, to your processor, to produce the output. Questions on that process? So this is why you have to do two steps to run your program if you're using C, because C itself is not being itself processed by the CPU. Questions on that? And so this is a compiler. And this style of language implementation is like translation, just like translating between two human languages. You hope your translator will preserve the meaning, the same behavior or meaning of that language, but it's being uttered in a different language, being stated in a different language. And that's what compilers do. That's what the compiler program does. What makes this tricky to think about when we actually go to write our compiler is, where does this GCC machine come from? Or how is it being run? It's a program, right? You run it. So who runs GCC? Or in this diagram, what is running GCC? It's also running on the CPU. And GCC, like our compiler, also has its own source code. But let's get there in a second. This diagram will look much more complicated if we reflect that. But for the time being, just assume we've already got this compiler program, this compiler machine. Takes a program in C source code and produces an executable. That executable is then given to your processor, which takes the input and produces the output for you. Okay, so that's compilation in a very high-level diagram. And the requirement that we have on this compiler program is that, or one way to define this equivalence is that any input that the executable takes, any input that the C program and the executable takes should have the same outputs for both versions of this program. Okay, so an interpreter, in contrast, simulates the actions of the source instructions. So let's see what this looks like. So if we have something like Python, how do you run a Python program? You have to say Python and then the name of the program, right? That name of the program might be file.py. And any inputs you have effectively also go into the Python program, into the Python executable along with your Python program. And it's the Python program effectively that produces the output. So you see the distinction here? In one case, our C program's first being translated, and then the CPU is like our interpreter. The CPU is a physical implementation of a language interpreter. So the electrical engineers designed circuitry that would process this language, this machine code language. Given some input, it produces the output. In our interpreter, we just have some software machine, a machine that we wrote to run on a computer, that takes in our program and the input, just kind of like a CPU, and produces the output. Questions on this? Okay, so someone asked about Java. Java is something like a hybrid approach, although many interpreted languages work like this as well. The Java program is compiled by the Java compiler into Java bytecode, and then that bytecode is interpreted by the Java virtual machine. It's the VM. So I think if you take CS2, I think it's Java, right? So you do some Java. So it's a two-step process, but to run the Java program, you still need to run an interpreter, basically, the Java virtual machine. Yeah. Sorry, this one? This? Oh, sorry, this is Java C. Sorry for my bad handwriting. Java compiler. Okay, anyway, don't want to belittle this too much. So same constraint on the interpreter approach to implementation. The interpreted program should have the same outputs that the source program would. So every execution of this input and output when running the Python program here should actually have the same inputs and outputs that you define in this Python program. Yeah.
So would you say that compile languages kind of directly use the CPU while interpreted languages indirectly use?
It's kind of the. That's right. So I think that's right. What it said. So what it said is, a compiled language or a language where you have a compiler, you directly run the program on the CPU, whereas the interpreted language, you don't. The program is being run by another program, the interpreter. So strictly speaking, this Python program is being run on the CPU to produce this. And this compiler itself, this compiler is also being run on the CPU, to produce the file output. And just like all the programs that you write in C, this GCC program is the product of a compiler. So we have some source code for the compiler, and it gets compiled by some C compiler, let's say GCC, to produce the GCC binary. So this is called the bootstrapping problem. How do you create a compiler? If your compiler is written in C and you don't have a compiler yet, how do you get that first compiler? Well, you have to write it by hand in assembly. You have to write it in the target language first. But then eventually you can start actually compiling the compiler. And this is kind of the most mind-warping part about compilers, is that you've got the compiler itself, which is software, which is written in some language. Then you have the input to the compiler that your compiler has to process, and you have the output of the compiler. Potentially 3 different languages. So we have the input language, the output language, and the language you're writing the compiler in. So don't worry if this is confusing. We'll have a first project to get you started on doing a little language processing. We'll go over some basic language processing today. But this is the kind of fun and mind-warping part about compilers, the self-referential aspect of compilers. All right, questions on this so far? Yeah.
I did have one. So the .exe that you wrote on the files part, is that purely just for namesake, or if we were to go in to use this and pull out at that file, would it be an exe file?
So if you remember from the file systems lectures, the extension is irrelevant. I just put this here to make it clear that it's an executable, but this is totally optional. You could put whatever you want. You could not have it, which is the convention from GCC. I just wanted to make it clear that this is an executable file rather than some other kind of file. Okay, so let's look at language implementation. So how can we get this program? Let's say we're trying to produce the output of adding 1 and 2 together, taking for granted that we all know what these symbols mean. How can we get this to turn into machine code? Okay, so let me take this program and I'll show you what this does. Make sure this actually works. Okay, there's our machine code. Okay, so here's how we're going to write our first compiler. It's going to take in any single digit, the plus symbol, and any other single digit. And it's going to turn it into a machine language program that will compute what we expect this to be. So we're going to just assume we know C-style arithmetic expression syntax, more or less. And when we translate this, what should we get? We should get assembly code. And what should that assembly code do? That assembly code should compute the answer 3. So how do we do this translation? So first, we need to be able to recognize our inputs. We need to be able to read in our inputs. So first what we're going to do is we're just going to read in 3 characters. So getChar reads 1 ASCII character at a time. And we're going to assign to variables the place, the position, or role that each of those characters has. So we'll take the first character, we'll call it the left, assign it to the left variable. We'll take the second character and assign it to the operator variable. We'll take the third character and assign it to the right variable. Questions on that? We're just reading in the inputs as characters, 1 character at a time, and storing them in these 3 variables. Questions on that code? Questions on this code? I want to make sure everybody gets this before we move on. So right now in memory, we've got 3 variables, and they're storing each of these 3 characters in memory. So to produce machine code that computes 1 plus 3, we just generate 3 machine code instructions every time. We generate, let me show the actual output. We generate a move. Wait, why didn't this get outputted? Okay, there it is. So we generate a move to a register, move number 1 to a register, move number 2 to a different register, and then we call the add instruction. Questions on this? This is x86 assembly. We'll look at this a little more when we get into the compiler. But I think everyone took computer organization, knows about registers, knows about machine instructions. So this is just storing the number 1 into a register called into the A register. This is storing number 2 into the B register. And this is adding the A register and the B register together, storing the result in the A register. I know the syntax may be unfamiliar if you haven't seen Intel, but that's what each of these instructions is doing. Yeah.
The dollar sign, I remember what it does, saying it's a value instead of
Yes, so this is the immediate store or immediate move. I don't exactly know what you learned in computer organization, but it's called an immediate.
Yeah, in computer organization, we learned MIPS, and MIPS there's a separate, well, there's not a move instruction, but there's separate immediate instruction. But we didn't learn about that dollar sign. I just remember it because I remember I was looking at like Game Boy assembly or something.
Yeah, so MIPS will have a different syntax, and this is, even x86 assemblers have different syntax. This is the GNU AT&T syntax, the syntax that the GCC compiler will use. But this is move immediate value 1 into the A register. This is move immediate or store immediate value 2 into B register. And this does A equals A plus B.
So if you didn't have the dollar sign there, it would be like move whatever is in memory.
Yeah, it would be address 1 without the dollar sign, yeah. We'll go over the various addressing modes and syntax in Intel. It's a little onerous. So MIPS, you learn a reduced instruction set. So Intel is CISC. It has a lot of different modes for all of their operations. Yeah. Say again? This happens. So ask again when we get into parsing. So or ask me during office hours. So the pre-processing stuff is a feature of C that is pretty specific to C, and it happens before parsing even happens. But we'll get there next time in the next couple of lectures. And ask again then, or ask on EdStem, and I can point you to that. So I do like research on pre-processing and parsing, and I'm happy to talk to you for hours if you want about this. But yeah, ask later when we talk into parsing, and I'll show you that stuff. Okay, so what does this program do? It reads in some ASCII characters, which themselves have no meaning. right? Like the ASCII code, I think we showed this, the ASCII code for the number 1, which one's decimal? The ASCII code for number 1 has a machine number value of 49. So this is the ASCII symbol for 1. If we were to print out the numeric value of this character, it would be 49. It wouldn't be 1 because it's an ASCII code. So what does this program do is it generates via this template code assembly instructions, and it just populates the places in the template, like here and here, and this add instruction, it populates them with values from the input. So at its simplest, what a compiler does is it has some templates for what each of the input constructs are supposed to do, and it has templates in the output language, and it just fills in those templates. So that's one simple way to write a compiler, but what this is doing is it's taking in our input language, which has no meaning to the machine, and it's generating a new program. It's literally just printing out code. And it's up to us, the compiler writer, to make sure that this code that's being output matches what the input program is supposed to mean. And in fact, if you don't have any other description of what this input is supposed to mean, this compiler is, in a sense, the definition of what that input program means. Questions about this program, what it does, how it works? So I'm literally just reading in 3 characters and then checking whether operator is a plus, and then just spitting out this assembly code that will add 2 numbers together if our operator is a plus. And it takes those 2 numbers from the input. Yeah? Change, instead of just standard out, redirect to a file. But that would be equivalent to just doing this, right? I can just redirect to a file on the command line, and then yes, you would just have your output stored in out.s. Yeah. Other questions on this program? Okay. So we've written our first compiler. Our compiler will translate addition expressions into assembly machine code. Not too hard, right? You literally just read in text and you write out text. And voila, you've got a compiler. As long as the input programs mean the same thing, then you're good. You've written the correct compiler. Okay, let's distinguish this from an interpreter approach. So let's take this interpreter program. And let's instead write an interpreter. It starts, let me make sure this actually works. Okay, we get 3. Okay, so it starts the same way. We have to read in the input. The input is just ASCII. Just ASCII. Does anyone not know what ASCII is at this point? Anyone wants to ask? So ASCII code is just the numeric conventions for the symbols we have that will be printed out to you by editors and by the console. And so we just read in those characters. They're just ASCII characters. And we have a similar construct here. We check whether we have the plus operator, the plus symbol for our operator character. If it is, then we convert the ASCII code into machine code numbers. So this is the quick and dirty way to do that. I could show you this using this special macro here, but basically we want to convert the ASCII digits into machine numbers. So this will convert the ASCII code for whatever, say, 1 is, into the actual number 1. And then instead of generating code, we write C code in our interpreter that will perform the addition, and then just print out the result of that addition. Questions on this and the distinction? So when we run this program for 1 plus 2 or 1 plus 4, 1 plus 4, this gives us the output of executing the program. Whereas our compiler Our compiler doesn't give us the number 4, it gives us code. It gives us a new program. All right, questions on this? Just want to make that distinction as clear as possible. So interpreters produce and compute the actual value, the resulting value of running the program. Compilers give you new code. So this may seem like simple now, but when you go right to the compiler and you're writing your compiler, you might be thinking, how am I going to write a program that's going to say dereference a pointer? And you have to remember, the output program is not going to be the resulting execution of that program, which will give you the value. It's going to be equivalent assembly code that's going to say dereference a pointer. And so, yeah, this is the trickiest part to wrap your head around, is that the compiler's goal is not to try to produce the answer. It's to produce a new program that, if you run that new program, it will produce the answer, the same answer as the input program. Yeah. That's a good question. So we'll talk about this next week. But this is the role of the assembler. The assembler is another program that will translate assembly code into machine code. And then we have a whole series of other tools that work together to give yourself an executable program. I have a lecture on that next week, next Monday, I think. And we'll go over the details of how that actually happens and it interacts with your system. But for now, and for our compiler, we're just going to target assembly language. And just use the GNU assembler to take us the rest of the way. All right, questions on this? Is this mind warping at all? Or no? So you're literally just writing print statements that will just print out code. It's just code generation. The tricky part is getting this right, getting it correct. Okay. So key difference, compiler programs prints out machine code that will compute addition if you run it on the machine, and the interpreter program will actually perform the addition operation and give you the answer. Oh, I lost connection with my notes. Okay, but what about, say, go ahead.
Like in a C program, like actually wrote 1 plus 2, it wouldn't like be adding 1 and 2 in like the program code itself, right? It would just put 3 is the execution.
Yeah, so what was asked is, if you actually do this in a C program, will it produce code like this, where it actually it generates an assembly addition? If you turn off all optimizations, actually no, I think even this can't be turned off, it will actually just generate 3 for you. It will do interpretation in the compiler. This is called compiler optimization. And this is why the distinction between compilers and interpreters is not so strict. That all compilers are doing some interpretation when it can, just to reduce the number of instructions at runtime. It's called optimization. And interpreters are almost always doing some compilation to a simpler language to reduce the work of what the interpreter has to do.
Make the most efficient compiler of all time by calling everything undefined behavior, letting you optimize all of the code away.
Yeah, I mean, if there's no definition of the meaning of the language, you could generate anything you want. Yeah. So if there's no, it would be the most, yeah. So take my graduate compilers class. I think it's going to be offered in the fall if you're really interested in the deeper insights into the compiler. But undefined behavior is a tricky one. You can do anything you want as the compiler writer. Undefined behavior is things like reading an array out of bounds. Okay. So what happens when we want to interpret something that our language we're writing the interpreter in doesn't have? So C doesn't have exponentiation. Let's say we wanted to add exponentiation to our language. But in our previous program, we just interpreted this by using C's own addition. How could we do this in our interpreter? Yeah.
You're going to need a loop and a lot more addition.
A loop and a lot more addition. So you can simulate exponentiation, even if your language, like your processor, doesn't have exponentiation, or at least not the general exponentiation, at least the Intel processor. And same way, our C language doesn't have exponentiation. So exactly right. So we simulate it. So this is the pseudocode for this. We do the same thing. We read in the operators and operands. And we check for our exponentiation operator. And we can't just say left caret right. we have to write the algorithm that emulates the behavior of exponentiation. So that's what the interpreter would look like. And so for homework tonight, I've given you the exercise of actually writing an interpreter based on this code here that supports exponentiation and modulo and subtraction and a whole bunch of other operations. Hopefully that's fast, but this is the pseudocode for doing exponentiation. Questions about this code here? So actually it's not addition, it's multiplication. But you can always emulate multiplication with addition as well. Questions about this code? So let me walk through it quickly. So to compute an exponentiation is just several multiplications. If you have 2 to the 5, it's saying multiply 2 by itself 5 times. That's what that's the definition of exponentiation. And so that's what this algorithm does. It starts with 1, and then from 1 to whatever the right operand is, like 5, it multiplies your result by the left operation, 2. So if I have 2 to the 5, I take 2 and I multiply it by the result 5 times. And that gives you, of course, 32. Is this the only way to emulate exponentiation? No, there's lots of ways to do it. You can use shift if you have a shift instruction in your machine and you have an exponent of 2, you can use shift instead. All right, questions on this interpreter pseudocode? All right, so let's make this a little trickier. How would you write a compiler for a language that has exponentiation? Intel x86, MIPS, they don't have exponentiation in general for your machine. How would you write a compiler to do this? Yeah. It's a lot of multiplies. Well, okay, so one way to do it is a lot of multiplies.
If you don't have multiplication, you have to do the addition. I remember this from your logic organization when we had to program this.
So let's assume we have multiplication. We have what your MIPS or your Intel instruction set has. Yeah. How would you do this? Oh, sorry. Did you have a question? Oh no. Okay. Okay. So let's take a look at what this. Let's take a look at what this looks like. So I think I have the whole program here. So I've altered my code a little bit, but it's the same idea. When I have a plus, I just generate code that's going to take the 2 digits and put them into 2 registers, and then invoke the add instruction in my processor. I can't do that with exponentiation because I don't have a general purpose power operation in the Intel world. But I can I can write machine code that would do that loop for me. So let me first show an example of what the output looks like. Here is machine code that will do the exponent of 3 and 5. So here I have 2 registers, B and C, that hold 3 and 5. I take the A register and store 1 here, so this looks just like our exponentiation algorithm here. So this is our same exponentiation algorithm, but written in machine code. We'll learn more about the machine code later, but this is a compare and branch. Here's the multiplication. And here's the for loop subtraction. So we're going from right, whatever the right operand is, 5 to 1, or 5 to 0, and we're just multiplying however many times the right operand has told us to and here's our branch. So hopefully this looks a little familiar from MIPS. We have a compare and branch here, we have unconditional branches, we have subtractions and multiplications. But otherwise, this algorithm is the same as this. The difference is this is in machine code, and we didn't write code that will actually run this. We wrote code that will literally print out this machine code. Does it make sense? Questions on that? So we're writing code that will read this input, see that the user has asked us to generate code for an exponent operation, and then we've spit out assembly code that if you assemble and run that assembly code, will compute the exponentiation. So just as a little reminder, this is how this diagram fits in. The code on the left here, this is my compiler. That's what GCC is doing effectively. It's taking your input language, like 1-5, and it's generating machine code. It's not trying to compute the value. It's not trying to figure out what the value is. It's just generating code. It's generating new code. Questions on this? Don't worry too much about the details of this. There's some kind of hard to read printf formatting stuff in here. You know, this %C is just printing a character. And then, you know, to print out a % with printf, you need to put 2. You need to escape it with 2 % signs. But anyway, this is a C program that takes in 1-2 or any digit and generates this assembly code from this template. Can't tell if this is too easy or too hard. You're all very silent. You look a little stunned, maybe. Yeah.
Since we know how many multipliers we're using at compile time, shouldn't we just get rid of those?
So another good question about optimization, since we know here in the compiler, like when we run our compiler, we can just look, oh, hey, the user has given us the number 5. Let me just compute, using our interpreter approach, the value of this. So that works if the compiler knows the value. The hard part is that the compiler may not know all the values at runtime. So for instance, if it asks from the user, what's the value of this? Asks for the user, give me an exponent. And that's read from the input, so your compiler not only has to work for one particular input, it has to work for all of them. And so to do that, it's very, very difficult to write a compiler that at compile time will deduce the value in all cases of every input. Or if it's, say, to a variable, say it's 3 to x, and x comes from a pointer somewhere, or x is also computed, then you may have some very complicated chain of computation you have to figure out at compile time for all possible inputs to the program. And if you take maybe discrete 2 or theory of computation, you may learn about the halting problem and Turing's solution or non-solution to the halting problem, disproof of the ability to solve the halting problem. So if you haven't heard of this, it's basically that some language properties, like is this computing an exponent, or does the program ever terminate or have an infinite loop, in general, under a general theory of what computation is not possible to do in all cases. So this is one of the main theoretical limitations of compilers, is that we can't know at compile time what the value of all variables will be for every execution of the program. If you're really interested in that kind of theoretical side, or the theory of computation side, you can take graduate theory of compilers, take discrete 2, or take my compilers class, and we'll go into those challenges. But for this class, we're going to solve this in a very easy way. We're just going to have predefined templates for what the output code will look like that work for all possible inputs. That will make things easy. If you want to learn about optimization, how we can actually figure out constant values, take my graduate class, I go into optimization, and there's some cool math to do that. Yeah? I think it's programming languages and discrete 2 for it. And it used to be taught in the spring. I'm moving it to the fall, and then we're adding a advanced graduate class on like language translation next spring. Okay, so that's the simple technique. Well, I shouldn't say simple, but that's the technique we're going to use to make our compiler work in all cases. We're just going to have a predefined language template, which I'll give you, and then you'll have to write code that will generate the output code that basically defines the meaning of the input program. Yeah.
After this code is generated, then the assembler.
That's right, yeah. So for the purposes of this class, the assembly language is machine code. That's going to be the target language, the output of our compiler. And we're just going to use existing system tools for turning that into an executable. So I'll go over next Monday how that process happens, and our compiler is going to fit at the compilation phase. The rest of those are not technically not compilation, so that's called assembly, turning the assembly code into machine code, and then there's a bunch of other stuff at the system level that happens to give you an executable program. And someone else asked about the preprocessor. You can think of that as happening before compilation. And if there's time next week, ask me about that again, and we can go into what the preprocessor does. I can talk far too long about the preprocessor because I had to do research on it. Yeah.
So there's a compiler class, there's an assembler class.
There's no assembler class. I think in the catalog there may have been at some point, but compilers and assemblers usually go together. Assemblers is a kind of proto compiler. It's a type of compiler that it translates, and some assemblers do have some pretty compiler-like behavior. But yeah, for compilers, we're going to take the assembler for granted. All right, other questions on this distinction between compilers and interpreters? Yeah.
So I know sometimes like Python libraries are like native C or C++ code. How does that work? How does that
So a question about how does language interoperation have our native libraries? Again, another topic probably too long for this class. But I guess effectively the Python interpreter itself, because it's written in C, will just call a C function. And there's some sophisticated machinery that you can use to define the Python wrapping for that C program. If you look up what it's called, Python wrapper or native library, you can see the machinery there. But effectively what it comes down to is just the interpreter. So here was our interpreter program here. If you had a native library call, you would just check here, is operator native, and then literally call to the C function that was compiled in that native library. It's basically what's going to happen. Yeah.
I know also there's something similar to C# and like specifically verse compiling, and like there's a version or something to it.
I don't know about C#, but C#, Java, any interpreted language these days has support for so-called native libraries, which are, in this diagram, code that's compiled to run on the processor would be a native library, and code that's run on the interpreter, that's the non-native, that's the interpreted language. So in this diagram where you've got, you can make this very, very complicated, but basically this Java VM will call out to a native library that is being run on the CPU. Let me know in office hours or at STEM. I'll give you some more details on this, but I get lots of feedback about going on long tangents. So happy to go into the tangent for you in office hours. But it effectively ends up becoming just like a function call from the interpreter to the native library. That's effectively what happens. Other questions on compilation versus interpretation, on the way this compiler program works, the distinction between the two, and the main thing I want to kind of drill into your heads is that the compiler is not trying to figure out the answer in general. Its goal is to generate a program in assembly that if you run that program will compute the answer. But the compiler's job, strictly speaking, it does not have to compute the answer. It's not trying to compute the answer. And in general, it can't. Okay, so here's my ad for the compiler construction class. If you're really interested in this stuff, I know not many people are, take that class. I think I'm offering next semester. All right. So let's talk a little high level about the organization of compilers. So let's just skip ahead. So there's two phases to the compiler: the front end and the back end. The front end is what processes the input language. In the context of our really basic compiler here, the front end of our compiler was this code. It just takes in the text input and stores it into some program values, stores it into some memory layout. And the back end of the compiler is here. The back end of the compiler is what takes this representation from the front end and spits out the target language. That's how compilers are typically organized. These days, modern compilers, kind of industrial compilers, have a so-called middle end. And in the middle end, instead of translating to instead of taking our C program, so this is our front end, this is our back end. So we have some representation in memory of our input program, and this produces our assembly code. Modern day compilers will add an intermediate step here called the middle end. And instead of directly generating assembly, it'll first generate a so-called intermediate language, an IR. So the output of the middle end would be something like file.ir. And the intermediate language is dependent on the compiler framework you're using, but it's a language that is like a machine code language, but lacking any of the specifics of any particular machine. So let me show a diagram from LLVM, a really popular compiler infrastructure for writing compilers. And so the LLVM compiler world can support a whole lot of input languages like C++, Python, Scala, and support a whole lot of back-end machines. And you could certainly just write a compiler for each of these cases. So what does a compiler do? It takes an input language, produces an output language. So let's say we wanted to write a C++ compiler that targeted ARM. Well, that would be one compiler, right? And then I want to have a compiler that generates C, takes C, and generates ARM as well. That's two compilers. So here I've got 5 input languages and 5 output languages. Well, I'd have to write 25 compilers in order to have a compiler for every combination of input and language, right? That's a lot of work. So instead what I can do is I could take these 5 input languages and translate them to the same intermediate output language. And then take that intermediate language and write 5 backends to generate machine code. So now I only have to write 10 halves of a compiler. I don't have to write 25 compilers. The design of this, again, this is more for an advanced class, but the design of this is really dependent on the compiler framework. So LLVM uses a design that's very suitable for being targeted by C-like languages and abstracts away most modern kind of consumer processors. So it has infinite registers, but it has branches and go-tos, doesn't have if blocks or anything like that, but it has infinite registers. Abstracts away how functions work, and kind of the details of this are pretty much outside the scope of this class, but this is the design we're going to take in this class. We're going to basically build the back end for an intermediate representation. We're not going to have to do front end compilation in this class. We're going to compile the IR to assembly machine code. This is the high-level phases of a compiler from the kind of classic Dragon Book compiler's textbook. And you can see this is the front end here. Lexical analysis, this is identifying the words in the language. Syntax analysis, this is identifying the grammar of the language. Semantic analysis, this is type checking. So this comprises the front end. And the front end generates intermediate code. Intermediate code kind of looks a little bit like C, but you don't have expressions, you don't have block structured programming. And then the back end produces machine code. This is, I guess, MIPS actually. I think this is MIPS, right? Does this look like MIPS? Something like that. One other benefit of having a separate middle end for an intermediate representation is that the optimizations we were talking about, where you generate assembly code that has fewer instructions or refers to memory less, code that will run faster, you can perform those optimizations for all machines. So assuming that all machines work pretty much in a similar way, you can reduce the number of instructions here at the intermediate representation phase before you actually even generate the backend code. So all the compilers for all these backends can share the same implementation for optimization. Okay, questions on this at all? Okay, so let me... All right, let me give a preview of what we're going to cover next time and then leave some time for the homework and the project. Let me just motivate a little bit what we're going to talk about next time. We're going to go into how we actually define compilers, and I just want to show you briefly what I mean. So question, what does this mean? What does this symbols on the screen mean? All right, yeah, who wants to take a stab at what this means? Yeah. Arithmetic expression. Why is it an arithmetic expression? Has numbers. So we kind of interpret this ourselves, right? We know what this means. What about, and like what's the, so what does this mean? So what is the result of this? So it's an arithmetic expression. What's the result of this, of interpreting this? Who says 7? Who says 9? No one says 9? Okay. If you wrote in Fortran like decades ago, you might say 9. All right, what's this mean? So some people say, so do we do 6 divided by 2 and get 3 times 3? Is this 9? It's 9, or is it 6 divided by 2 times 3? 6. Is this 1? Who says 1? Who says 9? Who's right? How do you decide who's right? Yeah, you have to define what this means, right? So we all have a built-in notion because we've been trained. But for those of you who can read this? Who knows what this means? All right, good. There's one person. So what does this mean? What does this mean? So you can guess, right? So if you're not the one, person who can read Chinese symbols here, so the person who can read Chinese symbols, what does this mean in Chinese? 1 plus 2 times 3, and the person who inferred it. So I just want to illustrate to you that to someone who understands this language, this means 1 plus 2 times 3. It means the same thing as this. But if you don't know what these symbols mean, it's gibberish to you. So when we're writing our compiler, what we're doing is we're giving meaning to these symbols. So we can't take for granted that this has a particular meaning. We can't even take for granted that 2 times 3 happens first. We can't take any of this for granted. We have to define what this means mechanically and then use that definition to write our compiler. So what gives symbols meaning? We give symbols meaning. We define what the symbols mean. They don't have intrinsic meaning, at least not according to my philosophy. So there's a common adage here: the map is not the territory. Confusing the moon for the finger pointing at the moon. Look up map is not the territory. It's kind of a classic philosophical question about symbols versus what they represent. If you rip up a map, you don't destroy the world. The map is just a symbol of the world. So it's the same thing here. Although we as humans who can process language kind of silently and automatically, we ascribe meaning to this without even realizing it. Okay, so that's a little preview from next time. Let me show you the homework and the project. First, we have this project to get you familiarized with the ANTLR parsing framework. There's also a reading here to read ANTLR. It's very short. Here's the instructions for doing it. There's 3 files that you need. One of them you have to hand type. This is an image, so you won't be able to cut and paste. It's part of the project to hand type it yourself. If you copy it from someone or cut and paste, that is cheating. So if you're discovered, you'll get a 0. So hand type this out yourself. It's very short. This is just to get you used to the ANTLR framework. And then there are instructions here for doing setup, compilation, and submitting as usual. Submit as usual. This is an exercise. It's only worth 4 points. Same rules apply for lateness. There's no lateness for the exercises because you literally just hand copy it. You've got a week to do it. And then our homework is what I described in class. Write an interpreter in C code, building off the interpreter that we had. Yeah, gotcha. Say again? Oh, the homework, yeah. Oh, yeah, it's supposed to be a 1. Yeah, you only need to support a single digit. Sorry about that. Uh-oh. And this doesn't work either. So I'll fix that. All right, other questions before we wrap up? All right, everyone, have a good week. I'll see you Wednesday.